Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we are going to discuss the chemical oxygen demand, that is COD, and its experimental determination. It is an important topic under a skill development program, and questions related to it are asked frequently in the examinations of chemistry, botany, geology, and biotechnology. Let us first of all introduce the chapter. The amount of oxygen required to oxidize chemically the oxidizable, biodegradable, and non biodegradable organic matter present in given volume of wastewater sample or sewage. Why a strong oxidizing agent to CO2, H2O, and other oxidized species under a specific conditions of temperature and time is called chemical oxygen demand, and it is abbreviated as COD. Let us see it again. The amount of oxygen required to oxidize chemically the oxidizable, biodegradable, and non biodegradable organic matter present in given volume of wastewater sample or sewage by a strong oxidizing agent to CO2, H2O, and other oxidized products under a specific conditions of temperature and time is called the chemical oxygen demand of the water sample, and it is abbreviated as COD. Expression of chemical oxygen demand and oxidizing agent used for the determination of COD. The chemical oxygen demand, that is COD, is expressed in milligram of oxygen per liter of water sample. COD is expressed in milligram of oxygen per liter of water sample, and it is also called part per million, that is ppm. In earlier days, KMnO4 was used as the oxidizing agent in the determination of COD, but COD values obtained in this way were much lower than fifth day BOD value. It means KMnO4 was not much effective in oxidizing all the organic matter present in the water sample. Modification in oxidizing agent. Thereafter, other oxidizing agents such as ceric sulfate, CeSO4 whole 2, potassium iodate, KiO3, and potassium dichromate, K2Cr2O7, were also used in the determination of COD. Potassium dichromate is the most effective oxidizing agent. Potassium dichromate, that is K2Cr2O7, is the most effective oxidizing agent in the determination of COD of water sample. Benefits of using K2Cr2O7 as oxidizing agent in the determination of COD. The use of K2Cr2O7 as oxidizing agent in the determination of COD has following benefits. K2Cr2O7 oxidizes completely all the organic matter present in the water sample. The second one is it is relatively cheaper and K2Cr2O7 can be purified easily. Due to these three features, K2Cr2O7 is generally used as an oxidizing agent during the determination of COD value of given water sample. Now let us see the determination of COD. First of all, let us discuss the principle involved in this process. An accurately known volume of water sample is refluxed in a medium acidified with Kong sulfuric acid with known excess amount of K2Cr2O7 in the presence of HgSO4 to neutralize the effect of chlorides and Ag2SO4, that is silver sulfate, as catalyst. A portion of K2Cr2O7 is consumed to oxidize organic matter present in the solution. Let us see it again. An accurately known volume of water sample is refluxed in a medium acidified with Kong sulfuric acid with known excess amount of K2Cr2O7 in the presence of mercuric sulfate, which neutralizes the effect of chloride ions, and silver sulfate, which acts as catalyst. During this process, a portion of K2Cr2O7 is consumed to oxidize the organic matter present in the solution. K2Cr2O7 reacts with Kong H2SO4 forming K2SO4, Cr2SO4 whole 3, water plus nascent oxygen. This nascent oxygen oxidizes organic matter present in the water sample to CO2, H2O, and other oxidized products. And thus, a portion of K2Cr2O7 is consumed to oxidize the organic matter present in the water sample. The unused or unreacted K2Cr2O7 is titrated against the standard solution of ferrous ammonium sulfate, which is abbreviated as FAS, using ferroin as indicator. To determine the amount of K2Cr2O7 consumed to oxidize the organic matter. When the given water sample is refluxed with K2Cr2O7 in medium acidified with H2SO4 in the presence of HgSO4 and Ag2SO4, the organic matter present in the water sample is oxidized to CO2, H2O, and other products. During this process, a portion of K2Cr2O7 is consumed to oxidize the organic matter present in the water sample, and the unreacted potassium dichromate is titrated against the standard solution of ferrous ammonium sulfate using ferroin as an indicator, and it is done to determine the amount of K2Cr2O7 which has been consumed to oxidize the organic matter. The amount of K2Cr2O7 consumed is equivalent to oxidizable organic matter present in the sample. According to law of equivalence, the number of gram equivalents of K2Cr2O7 consumed will be equivalent to number of gram equivalent of oxidizable organic matter present in the sample. Now let us see the reagents required for the determination of COD. 0.25 N K2Cr2O7 solution is required for this purpose, and this solution is prepared by dissolving 12.259 gram K2Cr2O7 in distilled water, and the volume is made 1 liter by adding more amount of distilled water. When 12.259 K2Cr2O7 is dissolved in distilled water and the volume is made 1 liter, we get 0.25 N K2Cr2O7 solution. The second reagent is 0.1 N, that is deci normal ferrous ammonium sulfate solution. For the preparation of this solution, 39.2 gram ferrous ammonium sulfate is dissolved in distilled water, and 20 ml Kong sulfuric acid is added to it to acidify the medium. Thereafter, the volume of the solution is made 1 liter by adding distilled water, and thus we get deci normal ferrous ammonium sulfate solution. Ferroin indicator is used during the titration, and this indicator solution is prepared as follows: 1.485 gram of 110 phenanthroline and 0.695 gram of FeSO4 7H2O, that is green vitriol, are dissolved in distilled water and the volume is made 100 ml. Thus we get ferroin indicator solution. Kong sulfuric acid is required with a specific gravity 1.84, that is density 1.84 gram per ml. Mercuric sulfate HgSO4 solid is required to neutralize, to cancel the effect of chloride ions, and silver sulfate, that is Ag2SO4 solid, is required as catalyst. Now let us see the procedure for the determination of COD of water sample. 20 ml water sample, wastewater or sewage water, is taken in a COD flask. 1 spatula HgSO4 and a pinch of Ag2SO4 are added to the flask. We have already seen that HgSO4 neutralizes the effect of chloride ions while Ag2SO4 acts as catalyst. Then 10 ml 0.25 N K2Cr2O7 solution and 30 ml Kong sulfuric acid are added to the flask. Let us see again 20 ml wastewater sample is taken in COD flask. One spatula HgSO4 and a pinch of Ag2SO4 are added to the flask. Thereafter, 10 ml 0.25 N K2Cr2O7 solution and 30 ml conc H2SO4 are added to the flask. The content of the flask is shaken well and then refluxed or digested for 2 hours. Thus, the volume of water sample is specified 20 ml, time is specified as 2 hours, and the temperature is the boiling temperature at which the refluxing has been carried out. The flask is then cooled and distilled water is added to it until the volume becomes 140 ml. 2 to 3 drops of heroin indicator are added to the flask and then it is titrated against DC normal ferrous ammonium sulfate solution. The end point is indicated by the change in color of the content of flask from, not from blue green to reddish brown. After digestion, the flask is cooled and distilled water is added to it to make the volume 140 ml. Thereafter, 2 to 3 drops of heroin indicator are added to the flask and then it is titrated against 0.1 N ferrous ammonium sulfate solution. The end point of the reaction is indicated by the change in color of the content of flask from blue-green to reddish-brown. Then 20 ml of distilled water is taken in the COD flask and a blank is run using the same quantity of other chemicals. This is called blank run and the reading obtained in this way is called blank reading. Color of solution at different stages are represented in the following diagram. This is the color of the sample before digestion, before refluxing. That is when water sample is mixed with H2SO4, K2Cr2O7, HgSO4 and Ag2SO4. The color of the content of COD flask is like it. And after refluxing, the color of the content of COD flask becomes blue-green. Sample color before end point after adding heroin indicator is like this. This is blue, this is blue-green. And at the end point, the color of the content of COD flask becomes reddish brown. Let us now see calculations, which is the most important part of any analytical method. 1 gram equivalent ferrous ammonium sulfate solution is equivalent to 1 gram equivalent K2Cr2O7. It is in accordance with the law of equivalence. 1 gram equivalent of ferrous ammonium sulfate will be equivalent to 1 gram equivalent of K2Cr2O7. And 1 gram equivalent of K2Cr2O7 will be equivalent to 1 gram equivalent oxygen. And 1 gram equivalent oxygen is equal to 8 gram oxygen, which can be written as 8 into 10 to the power 3 milligram oxygen, because 1 gram is equal to 10 to the power 3 milligram. Thus, we have seen that 1 gram equivalent ferrous ammonium sulfate solution is equivalent to 8 into 10 to the power 3 milligram oxygen. Volume of ferrous ammonium sulfate solution required to reduce the unused K2Cr2O7 solution is equal to VmL. That is, it is the titer value of ferrous ammonium sulfate solution for reaction with unused K2Cr2O7. Number of gram equivalent of ferrous ammonium sulfate will be equal to V into N by 1000. This is the general formula for the calculation of number of gram equivalents of solute in the solution, where V is the volume of solution in ml, N is the normality of solution. And we have already seen that 1 gram equivalent ferrous ammonium sulfate is equivalent to 8 into 10 to the power 3 milligram oxygen, and therefore V into N by 1000 gram equivalent ferrous ammonium sulfate will be equivalent to V into N by 1000 into 8 into 10 to the power 3 milligram oxygen. These two terms will be cancelled out and we will get V into N into 8 milligram oxygen. And thereafter the COD value of water sample is calculated using this relationship, V minus A into N into 8 divided by volume of sample in ml divided by 1000. This is the volume of sample in liter. VmL, water sample, has been divided by 1000 and it is the volume of water sample in liter. V, this is V, N into 8 and divided by water sample in liter. This is COD value of water sample in milligram oxygen per liter of the water sample. Here 1000 is in denominator, which comes to the numerator as followed. COD value is equal to B minus A into N into 8 into 1000 divided by volume of water sample in ml mgO2 per liter. This is the COD value of water sample. Here different terms used are discussed. A is the volume of ferrous ammonium sulfate solution required for blank in ml when 20 ml distilled water is used, and B is the volume of ferrous ammonium sulfate solution required for sample water in ml, that is for 20 ml water sample. B ml ferrous ammonium sulfate solution is required, and N is the normality of ferrous ammonium sulfate solution. Limitations of COD determination. The aromatic hydrocarbons and pyridine, if are present in the water sample, they are not oxidized by potassium dichromate. And if the sample contains more than 2000 ppm of Cl minus ions, COD cannot be determined accurately because a portion of K2Cr2O7 is consumed to oxidize Cl minus ion to Cl2. A portion of Cr2O7 2 minus ion is consumed to oxidize chloride ion to Cl2. Thus, the COD value becomes greater than that expected to oxidize the organic matter present in the water sample. Thank you for watching the video with patience and concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.